Welcome to Algebra 2. Today we've got section 6.6, solving exponential and logarithmic equations. All right, now we just got done going through section 6.5, which covered a lot of properties of logarithms, and we've discussed properties of exponents. You covered them a lot in Algebra 1, so we took a lot of that prior knowledge and built upon it in the last section a little bit with some information about logarithms, how to combine them together. So today we're going to use those properties to help us solve equations that involve exponential and logarithmic functions. Let's go ahead and get started. All right, first, dealing with exponential equations. These are equations where the variable we're trying to solve is an exponent. So our properties of exponents are going to be really, really helpful in order to help us rewrite and make the overall equation easier to work with. We've got three options. So anytime we're dealing with an exponential equation, we want to kind of look in this order because we have methods of solving each one. But if we can manage to find one of these steps that's higher on the list, it's going to be an easier problem to deal with. The first and easiest method, if it works, is can we use our properties of exponents to rewrite the equation so that we have both sides of the equation as the same base raised to different powers. This is called the common base method, and it really makes an easy problem out of a very difficult one. So naturally, we want to look for this one first. This one's especially, it should be something that we can recognize pretty quickly, make a couple tests in our calculator maybe, but we'll pretty quickly decide whether or not we can use that method. Secondly, is there only a variable in one exponent? So we can't use common bases, maybe that doesn't work out. If there's only a variable in one exponent, everything else is just a number or something else that we can work with, that's when we use log base. This is a feature on most newer calculators, and it allows us to use the idea that logarithms and exponents are inverses of one another in order to get to that exponent. So that's our next fastest method. If we couldn't use common bases, then log base is the way to go. Then lastly, if there is any other type of exponential equation, maybe we have different bases, but we have variables on both sides. Maybe it's a complicated problem involving like compound interest or something we're trying to solve for a variable in the exponent. Then our best bet is to use what I call log free the exponent. And what this means when I say log, we can annotate our notes a little bit here. We're going to take the natural log of both sides. Because one of our properties, let's say we natural log one side of the equation, and we have the natural log of what was 3 to the x minus 4 power. If I take the natural log of that side of the equation, I'm allowed to free that exponent, and it becomes just a regular term out in front that we can solve for. In the calculator, we can easily type in natural log 3. So it takes that exponent and makes it something that we can work with. So that's our last resort option. It's typically a little bit more writing, but it will solve just about any other type of exponential equation. All right, what about logarithmic equations? Well, we covered all those properties that we had in 6.5, and we can bet that we're going to use quite a bit of them, as well as the definitions of a logarithm. The base is the perfect exponent that will turn the base into the argument of that logarithm. Now, one thing we're going to have to be sure that we check our answers because it is possible that we will get more than one solution. And when I get more than one solution, I just want to make sure that when I plug it back into the original problem, it doesn't make any negative arguments in that logarithmic equation. If it does so anywhere, it's not an acceptable answer. So we can have extra answers there. We want to be sure we're checking for those. We've got two options for solving logarithmic equations. The first one, if I have some terms in the equation that are logarithms, others that are not, I call that iso smash def log. We are going to isolate, in other words, logs on one side. We're going to smash, that means condense, to a single log on that one side. And then the definition of a logarithm says that the base, the logarithm is that perfect exponent, it is x, to get to that power. So b to the x would equal a. We'll use that to solve the problem. But I think having a quick, easy to remember, kind of a memorable little slogan for this type, ISO smash def log, is a nice way of kind of saying, oh, okay, yeah, I know how to do this, ISO smash def log. It makes it easier to remember. The other option, well, what if all of the terms are logarithms and they have to have the same base for this to work? Then we're going to take both sides, smash the left side to 1 log, smash the right side to 1 log, and then we drop the logs entirely, and it just becomes argument equals argument. Typically a very easy equation. This second option, if we do see an equation that's set up this way, is much, much faster. Provided, of course, that we do all of the work with the properties to combine all the logarithms together. All right, so we've got quite a bit on our plate, and we are going to take some time to learn this, so be patient with it. If you need to go back and see how an example was done, please, by all means, go through and do just that. That's the wonder of YouTube, is you can go and rewatch an example if it didn't make sense the first time. So I hope we take full advantage to understand this fully. This was one topic that when we had our final exam last year, students struggled with this one. So you can save yourself a little bit of heartache later on by investing a little bit of effort right now. So here you can see we've got 4 different exponential equations. The variable that we're trying to solve for is in the exponent in each of these problems. Let's take a look at how we can handle each different type. So we'll start off with problem 8 here. First, I'm going to check and see, can I write 6 to some power equals 36 to some power? Can I write that as both of those having the same base? Well, I know, and just kind of thinking up here in my head, that 6 to the second equals 36. Oh, well, then I can leave the left side alone, but on the right side, I can call that 36 6 to the second. It's just a substitution. But now look at the ultimate base on both sides is a 6. We've got a common base, and this is great because this is the easiest way to do that. I just need to know that when I raise a power to another power, I multiply the exponents together, and that requires distributing that power of 2 into that power of 3x minus 5. Let's see what that does for our equation. So now I've got 6 to the 2x minus 6 equals 6 to the 6x minus 10. Because they are both 6 to some power, if those terms are going to be equal, then the exponents have to match because the bases already match perfectly. All I'm really trying to solve is 2x minus 6 equals 6x minus 10. Subtract 2x from both sides, add 10 to both sides. I find that x equals 1. Okay, and I'll go back and plug that in. 6 to the 2 minus 6, that's 6 to the negative first. Does that equal 36 to the negative second? Yes, it does. We can run through a quick check in our calculator if need be. But we very quickly get to the answer if we are able to set up common bases. How about number 12? Well, 512 and 1/8. Well, 1/8, anytime I see a 1 over, I know I can use a negative exponent there. That's 8 to the negative first. You can just try and rewrite, kind of substitute in. And 512, maybe I'll test that in the calculator, see if that's 8 to some power. And hey, it's 8 to the third. So I'm able to get a common base. Even though it had a negative exponent on the right-hand side, it's still a common base. It still works. Feels like we're cheating the system because it's so easy. On both sides, we do have a power to a power rule to carry out. So I've got 8 to the 15x minus 3 equals 8 to the 4 plus x. Well, if those terms are going to be equal, their bases already match, exponents have to match. So my equation becomes 15x minus 3 equals 4 plus x. Let's subtract x from both sides, add 3 to both sides, x equals 1/2. And it's perfectly fine if we end up with an exponent that's not an integer. Here we've got a fraction. We know that fractional exponents are perfectly acceptable as numbers. They just mean roots. All right, now we get into some more interesting stuff. Those first two, we were fortunate. It may have taken a little bit of time, but we did find common bases, and that made the work very easy for us. For number 14, if you look at that, 11 to the 6x, there's no way I can write that 38 on the right as 11 to some power. Okay, so I cannot establish common bases. Then I look at, okay, is there only a variable on one side of the equation? And thankfully there is. So now I just need to think of, hey, the only problem is I want to get to this x right here, and it's an exponent on 11. So what would cancel out 11 to some power? Oh, logarithms. Logarithms. So I'm going to take log base 11 of both sides, and that's what we call using the log base method. On the left, log base 11 of 11 to some power is just the power. It simplifies away. All we're left with is that 6x. And on the right-hand side, I have log base 11 of 38. I couldn't simplify that, but you know what? My calculator can sure handle it. So all I need to do in the calculator is type in log base 11 of 38 divided by 6. And I'll get an answer of, type that up really quickly, I get 0.2528. All right, and lastly, let's go about problem D, I guess. It's the last example. I kind of added this one off the cuff. Can I get common bases? Well, no. That 4/5 is really kind of a pain in the posterior. Okay, so common bases are out. Is there an exponent only in one, or sorry, a variable in only one of those exponents? No. So log base is out, unfortunately. Luckily, we do have that one last option of log free the exponent. So I'm going to take the natural log of both sides. That's going to allow me to free the exponents. And let's see what that sets up. I've got 2x times the natural log of 4 equals x plus 1 times the natural log of 4/5. Again, since I'm using natural log, it's an easy type into the calculator. I don't have to go through any menus or anything. It's a key that's right there ready to use. It's just some decimal. All right, well, what I want to do is I want to group my x terms together. So I need to take this number, natural log of 4/5, and distribute that on the left, or on the right, I should say. 2x natural log 4 then equals x natural log of 4/5 plus 1 times the natural log of 4/5. Again, those are just decimals I can get out of the calculator. I'm going to subtract over this x term, right? I want to combine like terms. Let's get our x's grouped. So I have 2x natural log 4 minus x natural log of 4/5 equals natural log of 4/5. This is why it's our last resort. It does take a little bit more writing, but it's really not too terrible to do. Now, in order to get 1x to solve for, I can now factor it out as a GCF. X times 2 natural log 4 minus natural log of 4/5, I've factored it out, equals the natural log of 4/5 on the right. And all of this right here can be divided out. It is some number that my calculator can figure out. So I'm going to take the time to carefully group everything together, make sure that it's in the calculator the right way. All of that cancels out, leaving x on the left. And once I punch in natural log of 4/5 divided by that group, 2 natural log 4 minus natural log of 4/5, calculator comes out with a solution, negative 0.075. And we can round that to 4 places. Since it's an exponent, we want to be a little bit more precise than just like rounding to the nearest tenth or something like that. So an answer of negative 0.1 would be way off. So I typically choose 4 places when doing exponential equations. So there you've seen the good, the bad, and the ugly, the really nice way of using log base and common bases, and then if that all fails, then we do still have this method that will work every single time by logging both sides and freeing the exponent. All right, moving along. Now we got logarithmic equations. So for number 26, I just want to see, okay, do I have some logarithmic terms in that equation or all logarithmic terms? And in 26, you can see I've got one log and a regular number. Okay. Well, my procedure there when some of the terms are logarithms, is to isolate the logs. That's done. Smash them into one logarithm. That's done. And then use the definition of a logarithm. So I really only have to do step 3. The definition of a logarithm says that if I have a base of 3, the logarithm equals the perfect exponent to put on that 3 to turn it into, 2x plus 1, our argument. Well, I could give this to any freshman in Algebra 1 and they'd be able to solve this. 3 to the second is 9. Let's subtract 1 from both sides. Divide both sides by 2, and I find x equals 4. Now, I want to double check. Can I plug that in safely without making the argument negative? I plug in a 4, I get 2 times 4 plus 1, that's 9. Yep, it works. ISO, smash, def log. For number 30, okay, do I have all terms that are logarithms or just some of them? Here, all the terms in my equation are logarithms, and they have the same base. So this is really good. If one log base 6 of something equals another log base 6 of something, then their arguments have to match as well. So I can drop the logarithms out of the problem entirely, and I get 5x plus 9 equals 6x. We want to be really careful that there aren't any extra just regular numbers or anything hanging around. This only works if we have one logarithm equaling another logarithm. Okay, all I do to solve, subtract 5x from both sides, I get 9 equals 1x. X equals 9. Okay, well, let's double check. If I plug a 9 back in on the left, I get log base 6 of 45 plus 9, 54. And if I plug 9 into the right side, I get log base 6 of 54. Yeah, it works. No negative arguments. We get to keep that one. Alrighty. Next, we're going to up the ante a little bit. You can see these equations have gotten a little bit more difficult. For number 36, I've got 2 logarithms added together. Even though it's ln, that just means a logarithm base e, remember, so we can use all our properties still. 2 logarithms added up equals a regular 5. So not all the terms are logarithms, just some of them. So I want to isolate the logarithms. Well, that's already done. They're grouped together on the left. I want to smash the logarithms, condense them into one, and that's where I need to pick up the problem right now. So what I'm going to do is say, okay, I can write this as one natural logarithm. Since these were added together, it's the same as multiplying their arguments inside a single logarithm, and that's equal to 5. Okay, the smashing is done. Isolated, we smashed, now it's time for def log. So what this statement is telling me, and I can simplify it, call it x squared minus 2x. What this statement is telling me is that if I wanted to turn a base of e, and we have to know that that's a base of e in a natural log. If I wanted to turn an e into an x squared minus 2x, the perfect exponent, the logarithm, is a 5 to put on that e. Base of e, perfect exponent is 5 to get to x squared minus 2x. Okay. Now, it's my hope that you can get to this no problem. But once we get to this point, then it gets kind of tricky to actually find out, we're not done solving yet. We want x equals something. How do I solve something like that? Well, it sort of looks like a trinomial. And when we have a trinomial, we want to get it set up equal to 0. Remember all that lovely work from chapters 2, 3, and 4. So I'm going to subtract over e to the fifth. And then we can use quadratic formula. E to the fifth is just a number. So to find my solutions x, I've got the opposite of b plus or minus the square root of b squared minus 4, let's group that, 4 times a times c all over 2 times a. And if you've been following along in our calculator tips and tricks section, we made a quadratic formula program. So I'm going to use that right now just for sake of time and space here in these notes to solve this. Quadratic formula, my a value is 1, my b value is negative 2, c value is negative e to the fifth. And I get two solutions. I get negative 11.22 and positive 13.22. And let's just double check, because I don't know if I can keep both of those answers. If I plug them back into the original, well, if I try and plug in negative 11.22, it's going to bother this logarithm and this one. It will make both of them have negative arguments, so I cannot accept that answer. However, 13.22 will keep both of those arguments positive. That is our solution. Yikes, that had a lot. Another nice thing to consider is we did talk about, I believe it was when we were solving polynomials, or maybe it was with some work in chapter 5 with radicals. We talked about our life hack method. You know, say we get started on this problem and we get to a point where we're like, oh man, I have no idea how to solve this, or maybe we get to this step, I have no idea how to solve that. Well, what we could do is we could say in our calculator y1 equals natural log x plus natural log of x minus 2, and we could set y2 equal to 5 and do calc intersect. That would quickly point out this 13.22. That's a really nice last resort, especially like on a SAT test or in a test-taking situation. If we don't know how to do it algebraically, calculator can provide some really good support there. That's why I call it the life hack, really. All right, problem number 40. Here we've got all terms that are logarithms. Okay, so I'm thinking smash, smash, drop the logs. How would I combine these logs on the left? Well, they're both log base 5 and they are added together. So that's the same as 1 log base 5 with those multiplied together, those arguments multiplied together inside. And to multiply, I would take a binomial times a binomial. I've got to FOIL those. So I'm going to save a little bit of time by foiling those immediately. On the right-hand side, to smash these two together, I know that's the same as 1 log base 5, and since those logs are subtracted, it's division in the arguments. 50 minus 2, or sorry, 50 divided by 2 inside would be 25. All right, look at the condensing that we've done. Now I've got 1 log base 5 equals another log base 5. I can drop the logarithms out of it, because if they're going to be equal, their arguments have to match. And my equation becomes x squared plus 5x plus 4 equals 25. Okay, we've got a trinomial again, very much the same situation we had up above. Let's get it set equal to 0. Okay, and our quadratic formula says that x is going to equal opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. All right, and we would simplify that to get our answers according to that calculator program. Let's use that again. That's why we made it in the first place. A is 1, B is 5, C is negative 21, and I get negative 7.72 and 2.72. Let's take a look at the logarithms we started with, make sure that our solutions would not produce negative arguments in there. And that negative 7.72, man, if I plug that in here, if I added 4, it would still be negative. Here, if I added 1, it would still be negative, so I cannot include that. My solution is simply 2.72. That keeps those arguments positive. That's our accepted solution. Now, keep in mind that as you're doing this, if you're just like, wow, Mr. Hartz, this lesson really went from 0 to 60 in a hurry, you're right. This is about as difficult a logarithmic equation problem as I could give to you. So I hope you can take a second and appreciate the work that we're able to do on these slides with these two examples, because we have a lot of different solving methods coming together here. And that's the important thing to take away, is look at how all this comes together so well. Learning logarithms doesn't mean we might not have to use quadratic formula or factoring or anything like that. It all kind of comes together, and I really like examples that do that. Our third example, you deposit $1,000 in an account that pays 3.5% interest compounded monthly. When is your account balance $1,200? How about $3,500? Okay. So here, what we want to do is realize that we're trying to answer the when question. In other words, we're trying to find the time at which that will happen. So compounded monthly is another big giveaway. We're going to be using A equals P times 1 plus R over N to the NT power. It's not continuous growth, it's happening monthly, so we need to use this formula. All right, let's start off trying to find the $1,200 answer. The amount coming out is $1,200. We put $1,000 in. The rate is 0.035. That's how I would write 3.5% as a decimal. And since it's compounded monthly, that means 12 compounds per year. And I'm trying to find how many years. Well, this is a situation where we're trying to solve for a variable that is an exponent. All right, we're trying to get to that t right there. First thing we want to do, isolate the exponential. Let's divide out that 1,000. 1,200 divided by 1,000 is 6 over 5. We don't really even have to simplify that. We're going to turn to our calculator eventually. All righty. That equals 1 plus 0.035. I could find out what decimal this means, but again, if I'm going to type it into a calculator eventually anyway, why bother going back and forth between calculator and paper? Next, what I'm going to do, I need to free that exponent. So I'm going to log both sides, and technically you could use that log base method if you so chose. I prefer to log both sides in this situation, but it's your call. That will allow us to free that 12t, that exponent. So on the left, I've got natural log of 6 over 5. On the right, I've got 12t times the natural log of 1 plus 0.035 over 12. And here is the variable I'm solving for. I can divide away everything else. I can divide out the 12 natural log of 1 plus 0.035 over 12. And that will cancel everything out except for the t on the right-hand side. Okay, so now this is what I'm typing in the calculator, and I haven't had to turn to the calculator yet in the problem. So as long as I'm careful with grouping, I haven't rounded anything that could change my answer, and I haven't potentially miscopied something if I typed something into the calculator early. When I type in that work that's in blue over there, I get an answer of 5.217. And that is a number of years. All right, now with your newer calculator, it's probably storing all of that work in it, which is really, really nice, because second, they ask us, how long does it take to get to 3,500? Well, all we're doing is we're changing this value right here from 1200 to 3500. So I'm going to go through the exact same math, except it's going to change that number. That's it. Instead of being 6 over 5, it's going to be some other number. So I'm going to spare you both the time and effort of writing all of this work out again. The answer to our second part of this problem, when I plug that in, is 35.845 years. And that answer makes sense. It should take a lot longer for that account to get to 3,500 as opposed to just getting up to 1,200. Long time with that low interest rate. Right, and our final example here, use a graphing utility or graphing calculator to solve this equation. And this is first and foremost, actually only, a life hack problem. You'll see that one side of this is a logarithm. The other side is an exponential. So I can't log both sides to free the exponent. I cannot use the definition of a logarithm here, because then I will get a term that's exponential and one that's just a regular x. So really, this is a problem where the only means of solving is to use that life hack. So let me bring up a calculator here. And what we're going to do is turn the calculator on, of course. In the y equals menu on the left side, I'm typing in log x for y1. For y2, I've got 7 to the negative x power for y2. I'm going to graph. It sure looks like they intersect at some point there. So then what I'm going to do is I'm going to go calc, intersect. The first curve, you can see nothing's showing up for y. I have to toggle and make sure that it is on that logarithmic graph. There it is. Second curve, my exponential falling to the right. It's already got that located, so I'll hit enter. My guess, I'm pretty close to where those are intersecting, I think, so I'm going to hit enter. And there I get the x value, 1.233. Well, let's say 1.2327. Again, perfect instance where the only way we can solve that problem is by using the technology to help us out. And I really think that's an important lesson to learn. Sometimes we get so hung up on pencil and paper. It's important, don't get me wrong, but it's easy to get hung up on that when technology can really help us out here. All right, that does it for section 6.6. Again, a lot of information. I know this was a longer video, but this is something that in the classroom we would spend a couple of days on. A lot of different skills to practice, a lot of different patterns to find. So I really hope you're devoting your time well, understanding the different procedures that could come into play, and really getting an understanding of how exponentials and logarithmics work together. They really are useful functions in the real world. So I hope you've taken something away from this. And yeah, that does it for 6.6.